So when we look at chemical bonds, I've already alluded to the fact that we're going to have to think about how those chemical bonds form, and in particular we're going to focus on the electrons. So we need to think about these electron shells and what it actually means to have these electron shells. I've already talked to you about it a little bit. We talked about the first shell closest to the nucleus would like to have 2 electrons. The second shell out from the nucleus, do you remember how many you wanted? 8. Good. Okay. And those are primarily the ones we're going to focus on. So here are the shells, or electron clouds. You see it referred to both ways. In this case, looking at them associated with their placement on the periodic table. So our first shell, hydrogen, we've seen that before. 1 single electron. Helium we saw before, 2 electrons. So here's carbon. We've looked at carbon before. We said 2 electrons in the inner shell, and then 1, 2, 3, 4 in this outer shell. Well, it would really like to have 8, right? So how could we get carbon to have 8 electrons in the outer shell? This is chemical bonding or compound formations. What we really want to do is fill that outer shell. And if it's something like carbon with 4 electrons in the outer shell, it wants to fill the shell, that shell so that it becomes less reactive. So in its current state with 4 electrons in the outer shell, carbon is very reactive. So it's looking to achieve balance. You can think about it that way. So this whole goal of this interaction and this combining of elements is actually to form chemical bonds that are going to stabilize or reduce the reactivity of an element. Okay, so that's really the goal. How are they going to do this? Well, they can share, they can donate, or they can take. So we've got some options here for what's going on. For hydrogen, carbon, sodium, we've got this unfilled outer shell. They're going to want to find friends. They want to be balanced. They want to be less reactive. And to do that, they're going to have to either share, donate, or take electrons. Electrons are our focus. And remember these little yellow things here with the negative sign, these are electrons. Okay? Now the other ones on the other side are very stable, unreactive. We look at helium and neon and argon. While we said these are not important for biology so much, they are very stable. Okay? And so our other unstable atoms want to achieve that state somehow, and they're going to do it through chemical bonds. One of the most common chemical bonds that we see is a covalent bond. This is bonding again 2 or more atoms into a molecule or compound, and when we do that, these covalent bonds are actually going to share. So we look at an equal sharing of these electrons around these 2 elements when they come together. So if we take 2 hydrogen atoms, we said before hydrogen's got 1 electron, we put them together, the electrons come together, and we've got 2 hydrogens here, but we've got 2 electrons now running around, the outside. Well, there's still only 2 electrons and to 2 hydrogen atoms, but the deal here is they're sharing. So it splits seconds, tiny, tiny fractions of time. This nucleus has 2 electrons. This nucleus then has 2 electrons. And it's back and forth and back and forth and back and forth. Okay? So in the long run, they're sharing these electrons so that they are actually going to be less reactive and more stable in their environment. Hydrogen we just looked at. Oxygen, O2, we see this all the time. Hydrogen will actually pair with oxygen quite nicely, form something like water. Very stable compound. Terrific. Carbon, we mentioned carbon had 4 electrons on the outside. It wanted to share 4 more electrons. Well, to do that, you give it 4 hydrogens, form something known as methane, CH4, and you can form a very, very stable compound in this regard. When we look at covalent bonding in water, we're looking at the idea that oxygen is actually going to be holding on to these electrons pretty heavily. I mean, oxygen is a bigger nucleus compared to a single little proton down here in hydrogen. It has a larger pull or attraction for these electrons. Oxygen is what we call an electronegative element, meaning that it has a very high likeness or affinity for electrons. It's going to pull them in. And when it does, it's pulling them into orbit more around the oxygen. So it's going to, those electrons from hydrogen, say it's these two, are actually going to spend more time around oxygen than they are around hydrogen. So what we end up with is this kind of odd positive negative relationship that we're going to have to look at. We're actually going to slightly polarize this compound just by shifting the amount of time electrons spend around each element. When this happens, we call this a polar covalent bond. So a polar covalent bond means that you have a very electronegative atom, like in water. Oxygen is always very electronegative. So if you see oxygen in a compound, you can assume that there is going to be some sort of polar interaction here. Nonpolar is like our hydrogen, H2. We've got one hydrogen. We said the electrons just kind of spin around the outside. Everybody's happy. There's equal sharing. This is what I refer to as joint custody here, okay? So everybody's sharing, everybody's happy. That's great. But this is what we see typically between elements that are the same. We don't often see this between two different elements in a compound. And what we look at on our table is that these elements way up here at the top corner have these great big black dots associated with them. The bigger this spot, the more electronegative the atom is. So do you remember when we looked at our periodic table what those elements actually were in that top corner? So this one, carbon, nitrogen, oxygen. Right? Hydrogen's over here. So when we look at these large electronegative elements, we're going to have to deal with them in biology. So here is a representation of what I was discussing when I said that polar or electronegative element is going to be pulling in the electrons to one side more. So we've got a slightly negative on our oxygen, slightly positive on the two hydrogens. We've essentially set up something that kind of looks like a battery, right? It's got a negative side and a positive side. We're going to take advantage of this. Why does this happen, remember? This is all because oxygen is highly electronegative. So you can associate this as electron hog. It's not going to share equally. It's an electron bully. It's going to pull in these electrons and really hang on to them compared to what hydrogen can do. Hydrogen's weak and wimpy. It's not going to be able to fight back. It will occasionally get an electron wrapping around it, but most of the time it's going to sit here without its electron. And if you take an electron away from hydrogen, you end up with a positive element because it's lacking that negative, right? Because hydrogen is one proton, no neutrons, and one electron. So if you take away that electron, it leaves us with one positive charge. So we get a slightly positive charge associated with it. This is important when we start trying to think about the fact that a glass of water is not a single water molecule. It is gazillions of water molecules. So this little d means partial. Okay, so it means we've got this slight or partial positive and negative charge going on, turns these guys into little magnets. And when we look at this in in biology, we are very interested in how water will then behave because of it. Water is amazing, okay? And it's all because of its polar covalent bonds. So it's this establishment of this positive and negative ends to these water molecules that actually allows water molecules to stick together. So they actually stick together by a second type of bond known as a hydrogen bond. So the bond of the water molecule itself, we said, is a polar covalent bond. So this is the bond within a single water, okay? But when we look at water plus water plus water, like I have in my diagram here, these dotted lines between the negative of one water molecule number 1, and the positive of water molecule number 2, that dotted line in between, that's what we call a hydrogen bond. So in a glass of water, you have two different kinds of chemical bonding. You have a polar covalent bond that holds the individual water molecules together. And then you have hydrogen bonds that are going to hold all those water molecules together inside that glass of water. The important part of this is, we will look at this later, water actually has surface tension because of this. So this is why you can see leaves and things floating on the surface of water. We'll talk about this water tension later and how it affects biology.